On the 8th of November, 1942, at 1 minute past midnight, the first keel plate of a new Liberty ship was laid down at Kaiser Permanente Metals Shipyard No. 2 in Richmond, California. 4 days, 15 hours, and 29 minutes later, the finished hull slid down the ways into San Francisco Bay. They christened her the SS Robert E. Peary. A week after the keel was laid, she was delivered to the Merchant Marine, fully fitted out. On the 22nd of November, she sailed out of Richmond for combat duty. She was the 47th Liberty ship built at that yard. Her construction time was a fraction of the industry average. She was built almost entirely by welding instead of riveting, from prefabricated steel sections built at inland factories and railed in. The press called it a stunt. Henry Kaiser called it an incentive ship. The German engineers who read about her in Wire, reports filed in Hamburg, in Bremen, and in Danzig called it something else. They called it a method they would have to copy. 2.5 years later, on the evening of the 30th of April 1945, the afternoon Hitler shot himself in the bunker in Berlin, a German submarine slipped her lines at Bergen, Norway. Her name was U-2511. She was a Type 21 U-boat, the most advanced submarine ever built. Germany had commissioned 119 of them. She was the only one that ever sailed an operational war patrol. 4 days later, with the war ending, she returned to Bergen without firing a single torpedo. The other 118 Type 21s sat at their docks. They were not seaworthy. The hull sections that the German shipyards had tried to copy from Kaiser's method had not fit together when they arrived for final assembly. The weld defects were lethal. The boats could not be sent to sea. This is the story of why an American engine, built in Detroit, could be uncrated in a Normandy field in the summer of 1944 and dropped into the engine bay of any Sherman tank in about 4 hours. And it is the story of why German mechanics, trying to do the same thing with a Panther tank built in their own country, spent their days hand-fitting parts that should have been interchangeable. In the end, the war was not won by the better tank. It was won by the better part number. You are watching WW2 Tales. To understand what stunned German mechanics in 1944, you have to go back almost a century and a half. In 1798, a Connecticut inventor named Eli Whitney signed a contract with the United States War Department to deliver 10,000 muskets. He promised the parts of those muskets would be interchangeable. A lock from one weapon would fit into any other weapon without filing or hand-fitting. In January of 1801, he gave a famous demonstration in front of President John Adams and Vice President Thomas Jefferson. He laid out the parts of 10 muskets on a table. He had Jefferson assemble a working firearm from pieces picked at random. It worked. It was also a fraud. The historian Merritt Roe Smith, in his book Harper's Ferry Armory and the New Technology, proved that Whitney had pre-selected those parts. He had hand-fitted them in his Connecticut workshop and labeled them for the demonstration. Smith concluded that Whitney purposely duped government authorities. The real breakthrough came somewhere else, and it came slowly. It came at the federal armories of Springfield, Massachusetts, and Harper's Ferry, Virginia. At Harper's Ferry, a gunsmith named John H. Hall, working under contract to the Ordnance Department, spent 20 years developing manufacturing methods that produced parts to such tight tolerances that the parts actually were interchangeable. The historian David Hounshell, in his book From the American System to Mass Production, calls Hall's 1819 breech-loading rifle the first product ever made in large numbers whose components could be freely exchanged with one another and still function. It had taken 20 years to reach that point, 20 years of jigs and fixtures, custom-built milling machines, and hardened steel gauges that an inspector could clamp onto a finished part to judge it in a single second. 20 years of rejecting parts that did not pass and dropping suppliers that delivered too many rejects. By the time the British held their Great Crystal Palace exhibition in London in 1851, American gunmakers were exhibiting revolvers from Samuel Colt of Hartford and rifles from Robbins and Lawrence of Windsor, Vermont. The British were stunned. They coined a phrase for what they were looking at. They called it the American System of Manufactures. Britain formed a committee, sent it across the Atlantic to Springfield in 1853, and placed orders for American machine tools to re-equip its own Royal Small Arms factory at Enfield. The technology that had begun in Connecticut and matured in West Virginia crossed back to Europe, but Europe never fully adopted it. European industry, and German industry above all, kept its old culture. It kept what the Germans called the Facharbeiter, the skilled craftsman, at the heart of every workshop. A part on a German lathe in 1905 was finished by a man with a micrometer and a file. He took pride in making it fit. The American part was finished by a gauge. When the Second World War began, that difference would decide the war. In May of 1940, German tanks rolled into France. Within 6 weeks, the French army had surrendered, and the British were evacuating from Dunkirk. President Franklin Roosevelt sat in the Oval Office and asked one question: who in this country could actually build the weapons America was going to need? The financier Bernard Baruch gave him the answer in 3 words. First, Bill Knudsen. Second, Bill Knudsen. Third, Bill Knudsen. William Knudsen was a Danish immigrant who had arrived in New York Harbor in 1900 at the age of 20. He had risen through the Ford Motor Company under Henry Ford himself, organizing the assembly lines at Highland Park that produced the Model T. He had moved to General Motors and become its president by 1937. He understood industrial production at a depth almost no other man alive understood it. Roosevelt offered him the job of running American war production. Knudsen accepted. He gave up a salary north of $300,000 a year as president of General Motors and accepted a federal salary of $1. Knudsen had a manufacturing creed. He stated it constantly. Speed produces nothing in manufacturing, he said. Accuracy is the only straight line to greater production. At the plants he had run, he was famous for confiscating hammers and files. If a part did not pass the gauge, it was thrown out. It was not adjusted, not tapped, not filed to fit. It was discarded, and the supplier was put on notice. Starting in 1940, Knudsen pushed that principle into every contract, every plant, and every supplier in the United States that wanted to build weapons. He needed tanks. The United States Army in 1940 had fewer than 400 tanks, almost all of them obsolete. He went looking for someone who could build modern medium tanks in volume. He went to K.T. Keller, the president of Chrysler. Keller agreed. Knudsen called Albert Kahn, the architect who had designed the Ford Rouge complex and the Highland Park plant. Kahn drew up plans for a tank factory on 113 acres of farmland in Warren Township, Michigan, just outside Detroit. Ground was broken in September of 1940. The first M3 Lee tank rolled off the assembly line on the 24th of April, 1941. The roof was not yet finished. They called it the Detroit Tank Arsenal. It was 5 city blocks long and 2 city blocks wide. It held 1,000 machine tools and 8,000 specialized jigs. In December of 1942, it produced 907 Sherman tanks in a single month. By the end of the war, Chrysler had built 25,059 tanks at that one facility and had refunded approximately $50 million to the United States Treasury for coming in under cost. Across the country, 10 other factories joined Chrysler in building Shermans. The Fisher Tank Arsenal in Grand Blanc, Michigan, run by General Motors, built 11,358. Pressed Steel Car in Illinois built 8,147. Pullman Standard in Pennsylvania built 3,426. American Locomotive in Schenectady, New York. Ford Motor Company at Highland Park. Lima Locomotive Works in Ohio. Baldwin Locomotive in Philadelphia. Pacific Car and Foundry in Bellevue, Washington. Federal Machine and Welder in Warren, Ohio. Montreal Locomotive Works in Canada. 11 plants. Between them, by the time the war ended, they had produced almost 50,000 Sherman medium tanks. The exact figure from R.P. Honeycutt's standard reference, the book titled simply Sherman, is 49,234. Here is the part that mattered. A tank built at the Detroit Tank Arsenal in Warren, Michigan, and a tank built at Pacific Car and Foundry in Bellevue, Washington, 3,000 miles away on the other side of the continent, used parts that interchanged. Bolt patterns matched. Mounting brackets fit, shaft splines aligned, the transmission unbolted and slid out as a single unit. The engine bay accepted any of 4 entirely different power plants, designed and built by 4 entirely different manufacturers. Inside the Sherman family, 4 engines, 4 companies, all fitting the same hull. That had never been done before. The first engine was the Continental R975, a 9-cylinder air-cooled radial that had started life in 1928 as an aircraft engine, the Wright J6 Whirlwind. It produced 400 horsepower at 2,400 revolutions per minute. Continental Motors built over 53,000 of them for armored vehicles at its East Jefferson Avenue plant in Detroit and at its plant in Muskegon, Michigan, roughly 7 times as many for tanks as Wright had ever built for airplanes. The Sherman installation added a power shaft-driven cooling fan and shroud to replace the airflow that a propeller would normally have provided on an airplane. The engine went into the M4 and the M4A1 Sherman variants. The second engine was the General Motors 6046 twin diesel. This was a pair of Detroit Diesel 6-71 inline 6-cylinder 2-stroke diesel engines yoked to a common output shaft, each keeping its own crankshaft so that either could run independently if the other failed. Total displacement was 850 cubic inches. Output was 410 gross horsepower. Total weight, just over 5,000 pounds. It went into the M4A2 Sherman. Almost 11,000 of those were built. The Marine Corps preferred them because diesel fuel did not burn as readily as gasoline when a tank was hit. The Red Army received almost 5,000 of them through Lend-Lease. A Soviet after-action report from the 5th Guards Tank Brigade, dated the 23rd of October, 1943, stated that compared to the T-34, the M4A2 was easier to control and more durable in long marches because the engines did not require frequent adjustments. The tanks, the report said, performed well in combat. The third engine is the one that, more than any other, showed what American industry could actually do. The Chrysler A57 Multibank. In 1942, the Army needed more tank engines than Continental or General Motors could build. Chrysler was asked to design one in a hurry. There was no time to draw up a power plant from scratch. So 2 Chrysler engineers, Harry Woolson and Mel Carpentier, took 5 Chrysler car engines, ordinary 250.6 cubic inch inline 6-cylinder L-head engines off the Plymouth assembly line, and clustered them around a central crankcase. The 5 engines drove a single common output shaft through helical gears. Total displacement, 1,253 cubic inches. Total cylinder count, 30. Carburetors, 5. Distributors, 5. Water pumps, 1. Total horsepower, 425. 5 car engines bolted to a single shaft. The most surprising thing about it is that it worked beautifully. The A57 Multibank turned out to be the most reliable tank engine of the entire Sherman family. Aberdeen Proving Ground data from 1944 showed that crews running the Multibank Sherman spent just 45 hours on engine maintenance during the test period. The figures for the other engines were 110 hours for the M4A3 with the Ford engine, 132 for the M4A1 with the Continental, and 143 for the M4A2 with the twin diesel. British crews running the Multibank reported a mean distance between major overhauls of 4,000 kilometres. Chrysler built 9,965 of these engines between April 1942 and September 1943. Almost all of them went to the British, who used the Multibank Sherman as the basis for the Sherman Firefly, the only Allied tank in the West with a gun powerful enough to reliably penetrate the front armour of a German Tiger or Panther. The 4th engine was the Ford GAA V8, and its origin story is one of the strangest engineering accidents of the war. In 1940, Ford had been developing a V12 aircraft engine, hoping to win a contract with the United States Army Air Corps. The contract never came. The Air Corps was committed to the Allison V1710, so Ford had a fully designed all-aluminum V12 with dual overhead camshafts and a 60-degree bank angle sitting in its engineering department with nowhere to go. The Army Ordnance Department asked Ford if it could be turned into a tank engine. Ford's engineers lopped 4 cylinders off the castings. They kept the 60-degree bank, the all-aluminum block, the dual overhead camshafts, the gear-driven accessories. The result was the Ford GAA, an 18-litre all-aluminum V. 8 with dual overhead camshafts producing 500 gross horsepower at 2,600 revolutions per minute, the engineering specification, in other words, of a modern Formula One engine. And Ford was building it at its Lincoln plant in Detroit in 1942 for installation in tanks driven through mud and snow. Approximately 28,000 were produced. They powered the M4A3 Sherman, including the Easy-8, the Jumbo assault tank, and ultimately the M26 Pershing heavy tank. 4 entirely different engines, 3 engine companies and 1 tank arsenal that built them, 11 assembly plants that received them. And whichever engine was pulled, whichever Sherman variant it was bolted into, it fit. The bell housing matched the transmission input shaft, the mounting brackets matched the engine bay rails, the cooling shrouds bolted up, the bolt patterns lined up, the hoses connected, the wiring harnesses plugged in, the parts dropped right in. In the orchards and sunken farm lanes of Normandy in the summer of 1944, the United States Army applied that principle in the field. The result, captured in an armored force reliability study quoted in Honeycutt's Sherman, came from the mouth of an anonymous American tanker. He said it was an easy matter to change an engine, that it took little more than 4 hours, and that it beat all hollow the best time for the Germans. How did one army do this when the other could not? The answer was in the system of organized maintenance the United States had built before the war ever started. Army maintenance was structured around 5 echelons. First echelon was the tank crew themselves, doing daily checks and lubrication. Second echelon was the unit mechanics, doing minor repairs in the field. Third echelon was the Divisional Ordnance Company, doing medium repairs in mobile shops set up under trees. Fourth echelon was the Heavy Maintenance Battalion at field army level, doing complete engine and transmission swaps, hull welding, gun replacement. Fifth echelon was depot rebuild, back in England, in Italy, or all the way back at arsenals in the United States. In Europe, the system answered to Major General Henry B. Saylor, Chief Ordnance Officer of the European Theatre of Operations. Saylor in turn answered to the Chief of Ordnance in Washington, Major General Levin Hicks Campbell, Jr. Campbell had taken over the entire Ordnance Department in June of 1942. His first general order on assuming office stated plainly that whenever a member of the Ordnance Department, regardless of rank, encountered red tape in conducting business, he was to throw the red tape out the window. Campbell concluded the order with the words, "Accept that, please," as a definite general order. Under Campbell, the Ordnance Department became a $30 billion a year industry. The cost of TNT fell from 55 cents a pound in the First World War to 6 cents a pound by the end of the Second. The cost of a Thompson submachine gun fell from $90 in 1941 to $21 in 1944. None of those numbers were achieved by working men harder. They were achieved by the relentless application of standardized parts in volume. In Normandy, Campbell's system met its first test under fire. The 526th Ordnance Heavy Maintenance Company landed on Dog Green Beach at Omaha on the 9th of June, 1944. Part of the company had been lost when LST-1006 was hit in the channel 2 days earlier. The detachment that made it ashore was commanded by Captain Francis F. Poppenberg, and within 48 hours of touching the beach, his men were working on shot-up Shermans. Poppenberg later received the Bronze Star with a citation that read, "Performed a heroic task in refitting, repairing, and keeping in operation badly needed tanks." Other units leapfrogged forward right behind the combat divisions. The 2nd Medium Maintenance Company, the oldest ordnance company in the United States Army, with a lineage going back to Chateau Thierry and the Meuse Argonne in 1918, opened the first forward ordnance shop near Montebourg by the 13th of June. The unit history records that they worked long after dark by flashlight in blackout tents. The 3rd Armoured Division's Maintenance Battalion landed on the 4th of July. They came ashore with their own M25 Dragon Wagon tank transporters, 12-ton tractors built by Pacific Car and Foundry that could haul a knocked-out Sherman from the front line back to a rear area collection point. At the collection point, the ordnance crews assessed each damaged tank. If the hull was repairable, parts were pulled from crates and the tank went back into service. If the hull was beyond repair, the salvageable parts were stripped out for use on other tanks, and the rest was crushed. The maintenance battalions improvised on the spot when they had to. In the third week of July 1944, an American cavalry sergeant named Curtis G. Coolin, Jr., attached to the 102nd Cavalry Reconnaissance Squadron, designed a steel hedgerow cutter from welded German anti-tank tetrahedrons that the Wehrmacht had left strewn across the Normandy beaches. The cutter was 4 steel prongs welded to the front of a Sherman, sharpened to slice through the dense earthen banks the Germans were using as defensive positions. The 25th Ordnance Heavy Shot Battalion, under Brigadier General John B. Medaris, built almost 300 of those cutters in 48 hours, and welded them onto 3 out of every 5 First Army Shermans in 1 week. They did it in time for Operation Cobra, the breakout that ended the stalemate in Normandy on the 25th of July. 300 custom-built field modifications, designed by a sergeant, mass-produced by a heavy shot battalion, in 48 hours, in a combat zone. Ordnance Battalion records from the official history on Beachhead and Battlefront, written by Leda Mayo for the United States Army Center of Military History, contain dozens of operations of this kind. Engine swaps, transmission swaps, gun barrel replacements, hull patching. The American maintenance system was not just keeping the Army moving, it was a second factory operating in the field, fed by an Atlantic pipeline that delivered identical parts that fit. By the autumn of 1942, the German Army had a problem. They had been fighting the Soviet T-34 medium tank since June of 1941. The T-34 had thicker armor, a bigger gun, and wider tracks than anything the Germans had in service. The Panzer III was outclassed. The Panzer IV was equal at best. Hitler ordered a new medium tank that would beat the T-34. 2 firms competed for the design contract. Maschinenfabrik Augsburg-Nuremberg, known as MAN, submitted one design. Daimler-Benz at its Berlin Marienfelder plant submitted another. Hitler personally preferred the Daimler-Benz design because it looked like a T-34. The Heereswaffenamt, the German Army Ordnance Office, picked the MAN design instead on the 11th of May, 1942, because the new Rheinmetall turret with its long 75mm gun would only fit on the MAN hull. The Panther had been chosen. But there was a problem. MAN alone could not build it in the numbers the Wehrmacht wanted. The plan called for 600 Panthers a month by January of 1943, so the Heereswaffenamt licensed the design to 3 other plants. Daimler-Benz, the firm that had lost the competition, was ordered to retool and build Panthers from MAN's drawings. Maschinenfabrik Niedersachsen-Hannover, abbreviated MNH, started Panther production in the middle of 1943. Henschel and Sohn at Kassel built Panther chassis, with turrets coming from the Wegmann firm next door and being mated together on the Henschel line. 4 plants licensed to build the same tank. On paper, this was reasonable. The Sherman, after all, was built at 11 plants. But the Speer Ministry had not understood what came next. The Heereswaffenamt assigned every Panther part a drawing number called the Gruppennummer. The historian Thomas L. Jentz, whose book Germany's Panther Tank, written with Hilary L. Doyle, is the definitive technical study of the vehicle, explains why. Jentz writes that the Gruppennummern identify the exact component parts belonging to each of the various Ausführungen of the Panther. The engineering disaster sits inside that sentence. The reason every part had its own drawing number was that the same nominal part, the same Ausführung A drive sprocket, let us say, was actually several different physical parts depending on which plant had built it and at which point during production. A Panther Ausführung. A drive sprocket built at MAN in October 1943 was not dimensionally identical to a Panther Ausführung, a drive sprocket built at Daimler-Benz in October 1943. They looked the same. They did the same job. But a mechanic in a recovery yard could not just pull one part and bolt the other on. The chassis number had to be checked, the drawing number verified, and the part fitted by hand if it would fit at all. Jentz and Doyle document specific variations across every Panther subassembly. Drive sprockets differed between plants. The commander's cupola changed from a drum-welded type to a cast type at one chassis number at MAN, at a different chassis number at MNH, and at a different chassis number again at Daimler-Benz. The Schürzen, the thin steel skirts that hung along the sides of the Panther to detonate hollow charged shells before they reached the main armor, used different mounting brackets at MAN than at MNH. The engine deck exhaust shrouds varied. The turret rotation drives varied. The hull machine gun ball mounts varied. In a 2011 interview, Thomas Gentz summarized what he had found in the German archives. He said, "Man did not care what a Tiger tank looked like. The assembly workers would assemble a vehicle with whatever was on hand and whatever was most easily accessible." He was not even talking about the Panther in that quote. He was talking about a different German tank built by the same firm. The principle ran across the whole of German armoured vehicle production. The Facharbeiter, the skilled craftsman, was at the centre of every assembly hall. He had his caliper, he had his file. If the part did not quite fit, he made it fit. He was a professional. He was proud. He was, in a sense, the best in the world at what he did. And he was the reason an American ordnance battalion in Normandy could swap a Sherman engine in 4 hours, and a German panzer division recovering a Panther in the Ardennes could not. The Panther was beautiful. It was lethal. The 7.5 centimeter Qual K-42 gun was the most accurate tank gun of the war. The frontal armor, 80 millimeters thick on the glacis at 55 degrees, was effectively impenetrable to almost every Allied tank gun in service in 1943. A Panther could destroy a Sherman at 2,000 yards. A Sherman firing at a Panther's front plate could rarely penetrate at any range. But the Panther had to be running for the gun to fire, and the Panther was rarely running. The engine that powered the Panther was the Maybach HL230P30, 23 litres of displacement, a 60-degree V12, water-cooled, gasoline, with a cast-iron block and cast-iron cylinder heads. Nominal output, 700 metric horsepower at 3,000 revolutions per minute. The engine alone weighed 1,200 kilograms, about 2,600 pounds. It was built at Maybach Motorenbau in Friedrichshafen, and after April 1944, also at the Auto Union plant at Chemnitz. The HL230 had been designed in a hurry. It was an enlargement of the earlier HL210, which had powered the first Panthers and the Tiger one. Engineers had enlarged the bore of the smaller engine to gain displacement, but they had kept the cylinder spacing the same. This meant the metal webs between adjacent combustion chambers were dangerously thin. Head gaskets repeatedly burned through, not at the perimeter where you would normally expect failure, but between the cylinders themselves. The result was catastrophic engine damage. That was not the only problem. The fuel lines in the engine bay leaked. The carburetors overflowed, soaking the engine compartment with raw gasoline. A spark from the magneto or a hot exhaust manifold turned the engine bay into a fireball. Panthers caught fire on their approach marches before they had ever fired a shot in combat. Soviet engineers at Kubinka, who got their hands on captured Panthers in 1943 and 1944, recorded failure modes including burnt head gaskets, burst connecting rod bearings, broken connecting rods, cracked cylinder sleeves, and water in the exhaust manifolds. The engineers at Maybach kept trying. In September of 1943, they added copper sealing rings to the cylinder head grooves, a fix personally suggested by Ferdinand Porsche. They reinforced the fuel pump diaphragm spring. In November of 1943, the factory locked the engine governor to 2,500 revolutions per minute instead of 3,000, which dropped the rated power from 700 horsepower to about 600 and reduced the Panther's top road speed from 52 kilometers an hour to about 45. A British interrogation of a captured Panther crewman in June of 1944 recorded that his battalion had been averaging only 450 miles between engine failures. That was not even the worst part. The worst part was the final drive. The final drive was the gearbox that took the engine power after the transmission and delivered it to the drive sprocket on either side of the tank. The Panther's final drive used a simple spur gear. Thomas Gentz wrote in Germany's Panther tank, on page 147, that the final drive was the weakest part of the Panther. He went on, "It was a risky proposition," Gentz wrote, "to use a spur gear system for transferring the drive power, especially considering that the available steel during the war did not have a particularly high stress tolerance. The cause of the failure was something Albert Speer himself admitted in his post-war memoir, Inside the Third Reich. The Panther had been designed as a 30-ton tank. Hitler kept ordering more armor and bigger guns added during the design process. Speer wrote that in the course of a year Hitler once again insisted on clapping so much armor on it, as well as larger guns, that it ultimately reached 48 tons, the original weight of the Tiger. The final drive had been engineered for a 30-ton tank. It was now being asked to transmit power through that same single spur gear to a 48-ton tank. Jentz documented that in March of 1944, 13 final drives were replaced in 30 Panthers in one unit, a 43% replacement rate in a single month of normal operation. After the war, French Army engineers evaluated captured Panthers at the Army testing facility at Vincennes. Their report concluded that the truly weak spot of the Panther was its final drive, which was of too weak a design and had an average fatigue life of only 150 kilometers, just over 90 miles. That was the distance a Panther could be expected to drive before the gears in the final drive sheared, and the steel that should have been used to make those gears properly hardened was running out. The Watertown Arsenal Metallurgical Examination of Enemy Ordnance, published in February 1945, recorded the steady decline of German armor steel. Before the end of 1943, German armor sections contained 0.3 to 0.55% molybdenum, a critical alloying element that gives steel its toughness. By 1944, the same plates contained only 0.15 to 0.25%. The most recently examined sections, the report stated, contained no molybdenum at all. The German alloy supply was collapsing. The huge Nikopol manganese mines in Ukraine fell to the Red Army in February of 1944. The Norwegian Knaben mine became the sole German source of molybdenum. The Petsamo nickel mines in northern Finland were lost in September of 1944, when Finland signed an armistice with the Soviet Union. The Balkans, with their chromium, were lost in the same autumn. Portuguese and Spanish tungsten shipments dried up in the middle of 1944 under Allied diplomatic pressure. By 1945, Panther front plates, supposedly the most invulnerable armor of any tank in the world, were spalling. When a Soviet 122mm shell hit a late-war Panther glacis and failed to penetrate, the plate itself often cracked from the impact, and large fragments broke off the back of the armor inside the crew compartment, killing the men who were supposed to be protected. These were the conditions under which Germany was building the most sophisticated tank of the Second World War. The Panther was scheduled to make its combat debut at one of the largest battles in human history. Operation Citadel, the German summer offensive of 1943, would attack the Soviet salient at Kursk in central Russia. 200 Panthers were issued to Panzer Regiment 39, known as Regiment von Laukert after its commander, Major Meinrad von Laukert. The regiment was attached to Panzer Brigade 10 under the elite Grossdeutschland Division in the 48th Panzer Corps of the 4th Panzer Army. The Inspector General of the Panzer Troops, General Heinz Guderian, had spent weeks trying to talk Hitler out of the offensive. Guderian believed the Panther was not ready for combat and that the entire German armoured force was being thrown away for nothing. At a meeting in Munich on the 3rd of May 1943, Guderian asked Hitler directly, "Do you believe, my Führer," he said, "that anyone even knows where Kursk is?" Hitler replied that he was quite right. The Führer added, "The thought of this attack makes my stomach queasy." The attack went forward anyway, 2 months later than originally planned, on the 5th of July 1943. The Panthers had begun to break down before they ever reached the assembly area. Several caught fire on the road march from the railhead. On the morning of the attack, 184 Panthers were operational, out of the 200 that had been issued. Within hours of the jump-off, 18 Panthers were lost on the first day at Cherkasskoye. On the 7th of July, 6 more burned out from engine fires during the approach march. By the evening of the 6th of July, only about 40 were still operational. On the 10th of July, Guderian made an inspection visit to Regiment von Laukert. His report, preserved in the Bundesarchiv at Freiburg, under the file RH10/64, recorded what he found. By the evening of the 10th of July, he wrote, there were only 10 operational Panthers in the front line. 25 Panthers had been lost as total write-offs, 23 were hit and burnt, and 2 had caught fire during the approach march. 100 Panthers were in need of repair. 56 were damaged by hits and mines, and 44 by mechanical breakdown. 60% of the mechanical breakdowns could be easily repaired, and were on the way to the front. About 25 still had not been recovered by the repair service. Out of 184 operational Panthers at jump-off, 10 were still in the line 5 days later. By the end of July, the regiment's overall operational rate had stabilized at 16%. A captured after-action report from Panzer Regiment 39, dated the 11th of July, summarized the engineering disaster in a single sentence. Until reaching the first preparation area, the report stated 50% of the vehicles were inoperative, 2/3 of them with engine breakdowns, and 1/3 with the lateral transmission system. Despite the breakdowns, the gun was so lethal that even a quarter of the regiment was inflicting serious damage. The 48th Panzer Corps reported destroying 559 enemy tanks through the 15th of July, of which 269 kills were claimed by Panthers. But that was the high water mark. Operation Citadel was called off by Hitler personally on the 13th of July. The Red Army began its own counter-offensive almost immediately. Of the campaign as a whole, Guderian concluded later, "By the failure of Citadel we had suffered a decisive defeat. From now on the enemy was in undisputed possession of the initiative." The Panther never fully recovered from the mechanical reliability problem. Right up to the end of the war, Panther final drives kept failing at that fatigue life of 150 kilometers. A strengthened final drive was not introduced until September of 1944, more than a year after the problem was known to German engineers, because redesigning and retooling it would have shut Panther production down for months. Instead, Panthers shipped out the gates of MAN, Daimler-Benz, MNH, and Henschel, with a known fatal weakness from the day they entered service to the day Allied infantry walked through those same gates. By May of 1943, the Kriegsmarine, the German Navy, was facing a crisis of its own. 41 U-boats had been lost in a single month, in the Atlantic convoy battles. The U-boat war was effectively over. Admiral Karl Dönitz, who had been commander-in-chief of the Kriegsmarine for only a few months, went to Hitler with a proposal. Germany would build a new generation of U-boats so technologically advanced that they would resurrect the Atlantic campaign. The proposal was approved on the 31st of May. Naval armaments were transferred from the Kriegsmarine's own construction office to Albert Speer's Armaments Ministry. The new design was called the Type 21. It had a streamlined hull form derived from earlier high-speed submarine experiments. It carried 6 times the battery capacity of any previous U-boat, giving it underwater endurance and underwater speed that no Allied destroyer could match. It could remain submerged for days. It could outrun a corvette underwater. It would have brought the Battle of the Atlantic back into balance if Germany could have built them in numbers. Speer hired a man named Otto Merker to organize Type 21 production. Merker was a truck builder. He was the general director of the Magirus worker firm in Ulm, which made fire engines and trucks for the army. He had never built a submarine. He had never built any kind of ship. He had been hired specifically because he was a manufacturing man, not a naval architect. Speer had decided that the way to mass-produce U-boats was to apply truck plant assembly methods to them. Merker decided that the Type 21 would not be built the way any U-boat had ever been built before. Instead of being constructed in a slipway from the keel up, the boat would be divided into 8 prefabricated hull sections. Each section would be built at a separate inland steel factory. Roughly 32 different subcontractor steel firms would produce sections in parallel. The completed sections would then be railed and barged to 3 final assembly yards, Blohm & Voss in Hamburg, A.G. Weser in Bremen, and Schichau in Danzig. There the sections would be welded together. Merker promised Speer the first boat would be delivered in April of 1944, and that production would ramp to 30 boats a month by autumn. The actual chief naval architect at the construction office, an engineer named Friedrich Schwerer, objected. He wanted to build a single prototype boat first, work the bugs out of the design, and only then go to series production. Schwerer's request was overruled by Merker on schedule grounds. No prototype was ever built. The first Type 21 went straight from the drafting room at the Ingenieur Buero Glukauf in Blankenburg into series production at 32 factories Germany had never used for submarine construction before. The disaster, when it came, was almost mathematical. The historian Marcus O. Jones, writing in the Naval War College Review in 2014, summarized what happened. The tolerances involved in submarine construction were and remain extremely exacting, Jones wrote. Type 21 hull sections were initially delivered to the shipyards with deviations of up to 3 centimeters in some cases, and had to be torn apart and reconstructed properly, with massive outlays of time and effort in the ways. Pressure testing revealed potentially lethal defects in the welding of the first boats, a result of poorly fitting components, new inspection standards, and construction methods unfamiliar to the facilities performing them. 3 centimeters. More than an inch of deviation on a pressure hull that had to hold against the weight of 200 meters of seawater. The 32 inland steel firms had been building structural steel for buildings and bridges. They had never welded a submarine. They did not have the right inspection equipment. The pressure tests at Hamburg and Bremen and Danzig kept revealing weld defects. The Kriegsmarine's manganese saving order of April 1944, which had altered the formula of the high-strength St. 52 steel used for U-boat hulls, made the welds even more brittle. Hulls cracked under test. Sections had to be cut apart and rebuilt at the assembly yards. Exactly the labor that Mercer's modular system was supposed to eliminate. Clay Blair, in his 2-volume history Hitler's U-Boat War, described the result in plain language. He wrote that the boat was hurriedly prefabricated in 32 factories, and the 8 major hull sections were crudely made and did not fit together properly. The reason they did not fit was that the inland steel firms had no central tolerance authority. There was no William Knudsen at Speer's ministry walking into a factory and throwing out parts that failed the gauge. Each subcontractor decided for itself what was good enough. Of the 119 Type 21 U-boats commissioned by the end of the war, almost none were operationally ready. The United States Navy's official War Damage Report No. 58, citing the Naval Technical Mission in Europe's Technical Report 312-45 from August of 1945, recorded that the boats were delivered by the final assembly yards, but none of them became operational due to hydraulic system defects. The diesel engines were fitted with superchargers that did not work. Designed horsepower of 2,000 fell to an actual 1,200. Designed surface speed of 18 knots fell to an actual 15.6, which made the Type 21 slower on the surface than a Royal Navy convoy escort. The hydraulic system that operated the diving planes, the rudders, and the torpedo tube doors was located outside the pressure hull, where it was exposed to seawater corrosion, and worse, could not be reached for repair from inside the boat. Only one Type 21 ever sailed an operational war patrol. Her name was U-2511. Her captain was Korvettenkaptein Adalbert Schnee. She left Bergen, Norway, on the evening of the 30th of April, 1945, the afternoon Hitler shot himself in the bunker. On the 4th of May, Schnee received Donitz's ceasefire order. By Schnee's later account, he had obtained an attacking position on a British cruiser at 500 meters, dived deep, and returned to Bergen on the 5th of May. He had not fired a torpedo. A second Type 21, U-3008, under Kapitänleutnant Helmut Mansek, sailed from Wilhelmshaven on the 3rd of May, 1945. She received the ceasefire signal while submerged near a convoy, made no attack, and surrendered at sea on the 11th of May. That was the operational career of the entire Type 21 program: 1 patrol, 0 torpedoes fired. A senior German naval engineer estimated after the war that each Type 21 had consumed armaments-grade steel equivalent to 30 German army tanks. Marcus Jones, in his Naval War College Review article, concluded that the program had cost the German war effort some 5,000 tanks, 5,000 Panthers, 5,000 Panzer IVs, at a moment when German army formations on both fronts had been reduced to skeleton strength. That is what happened when Germany tried to copy Kaiser. The Reich had no Springfield, no hall at Harper's Ferry, no inheritance of the gauge tradition. It tried to leap to mass production without ever having mastered standardized parts, and the leap killed it. By the spring of 1945, with the Reich in its final weeks, German army repair depots across Western Europe were full of broken Panthers waiting for parts that would never arrive. The German Panzer Commission's reliability census in January of that year had counted 500 defective Panzer IV final drives, 370 defective Panther final drives, and 100 Tiger failures, all waiting for replacement assemblies. The replacements never came. The factories that built them had been bombed or overrun or were producing at fractions of capacity because the steel and the alloys had run out. Across the front, Allied ordnance battalions were doing exactly what Campbell's General Order in 1942 had instructed them to do, throwing the red tape out the window, putting tanks back in the fight. When the war in Europe ended on the 8th of May 1945, the United States had produced 49,234 Sherman tanks, almost 90,000 armored fighting vehicles of all types, more than 30,000 heavy bombers, 2,710 Liberty ships, and over 150 aircraft carriers of all classes. The country had transformed itself in 5 years from a depression-scarred economy into the greatest industrial military complex in human history. After the war, William Knudsen was asked how it had been done. His answer became one of the most candid summations any production man has offered. "We won," he said, "because we smothered the enemy in an avalanche of production, the like of which he had never seen nor dreamed possible." He was right about the avalanche, but the deeper truth was that the avalanche had been built on a foundation laid down 140 years earlier. Springfield and Harper's Ferry, John Hall's breech-loading rifle of 1819, the American system of manufactures shown at the Crystal Palace, Henry Ford's moving assembly line at Highland Park, Knudsen confiscating hammers and files, K.T. Keller at Chrysler, Albert Kahn designing the Detroit tank arsenal, Campbell throwing the red tape out the window, Medaris building 300 hedgerow cutters in 48 hours. That was the system. That was the inheritance. When a Wehrmacht mechanic in a captured ordnance depot in 1944 cracked open the engine deck of a knocked-out American Sherman, lifted out the destroyed engine, and was handed a fresh one straight from a wooden Detroit crate, he saw something his entire industrial culture had never produced. He saw a part that did not need him. He did not need his caliper. He did not need his file. He did not need to spend 3 hours dressing the bell housing flange to make the new engine seat against the transmission. He just had to bolt it down. It dropped right in. The Panther, on paper, was the best tank of the Second World War. The Type 21, on paper, was the best submarine. Both were brilliant designs produced by brilliant engineers in a country that had given the world Daimler and Benz, Krupp and Zeiss, Bosch and Maybach. None of it mattered. What mattered, in the end, was whether the part dropped in or had to be hand-fitted. America had been answering that question for almost 150 years. Germany never answered it at all. If you found this story worth your time, consider liking the video and subscribing for more. We have more to tell about the men of the ordnance battalions, more about the Panther program, more about the Type 21. We will see you on the next one. You have been watching WW2 Tales.